Hello, everyone. My name is Adrian Ornelas, a first-year aerospace engineering major. I'm a part of the UCI HyperExcite team, and today we'll briefly go over researching the future of travel from a controls perspective. Before we start, I wanted to give you a bit of background so that you're familiar with the Hyperloop concept. The Hyperloop is a new form of travel, similar to the bullet train, and it improves on the concept by offering higher speeds, lower operating costs, and an environmentally friendly traveling experience. Given my specialization is in embedded systems, I'll briefly cover vehicle control systems. In vehicles like trains, cars, and the Hyperloop, safety is the most critical point in design. Having a safe, consistent operation of every actuation and sensor input is paramount in the design of the system. At HyperSite, we are a research project that rapidly prototypes versions of the Hyperloop project in order to publish and share our research for the field as a whole. In order to meet this requirement with our embedded system, our system must be able to accurately and precisely control the various components on the pod. Some of these include the DC electric motor, brakes, high voltage power systems, among others. But again, to reiterate, the most critical detail is safety of the team and people around us. Our design goal as embedded systems engineers is to develop a software and hardware system in order to ensure the safe and consistent operation of the Hyperloop pod. To expand on this, this is the heart and soul of our pod design, the finite state machine. This diagram has largely dictated the direction we took in implementing all of the software and hardware components together. Our finite state machine relies on the various onboard sensors to determine how to operate in a safe way. Some of the major sensor inputs that our design relies on are the inertial measurement unit, which measures linear and angular acceleration, the pressure transmitters, rotary encoders, which determine the distance the pod has traveled, temperature sensors, and the battery management system. And also, finally, the electronic speed controller. The primary way we went about creating the firmware on our embedded system has been through incremental testing and the modularization of our work. Doing it this way, we were able to have abstracted modules of our sensors and actuators that we can independently test and verify. We will also have constant verification that our sensor readings in our system are correct, and by extension, this will also minimize errors. In the following diagram, this depicts the advantages of using a modularized coding scheme in our software. By writing two independent methods that control different systems on the pod, we can bring them together with ease in a way that is significantly easier to verify for safety. Right here, you can see that we have a file named pressure transmitters, and over here, a braking base station. And through the import statement, we were able to import all of the functions and methods inside the files so that we can use them in conjunction with each other while still having the modularization from before. Going further to our results, unfortunately, because of the pandemic, we have not been able to assemble our pod as the labs at UCI have been closed for the entire academic year. We have, however, validated our design and are ready to deploy it when we get access to lab again. Now that we have largely finished our embedded design, we will largely be shifting focus to the software our team will be using. We are implementing a graphical user interface to remotely operate and monitor the status of all the systems. Additionally, we are also preparing to showcase our work to other teams at European Hyperloop Week event in Spain so that we can collaborate together on the Hyperloop concept. Over here are some of the references that I have relied on most throughout the creation of the embedded system. And finally, I wanted to reach out and give a special thank you to my closest colleagues who have really allowed my research to contribute to the project. Thank you, Professor Rangel, Mugarad, Mahek, Myron, and Nathan for making this all possible.